Welcome, weary travelers of the day, to this gentle journey through the cosmos. Whether you've arrived here after a long day that stretched your mind and body thin, or perhaps you've simply discovered that counting sheep feels far less magical than counting stars, you're exactly where you need to be. Tonight, we're trading earthly concerns for something infinitely larger and more peaceful, our home galaxy, the Milky Way. You've got nothing to do now but rest, nothing to solve, nothing to rush toward, nothing to fix or plan or worry about. Just let your breathing slow and deepen, feeling your body becoming lighter with each exhale. Feel gravity gently cradling you, softening its pull, as if you're already beginning to float among the stars we'll visit tonight. The day's weight is dissolving, atom by atom, until you're as weightless as the cosmic dust that drifts between distant suns. Tonight, we're embarking on a peaceful drift through the Milky Way galaxy, our cosmic neighborhood that spans 100,000 light years from edge to edge, containing somewhere between 200 and 400 billion stars. We'll explore the gentle mysteries that unfold across billions of years, discovering the quiet secrets hidden beneath the galaxy's serene beauty. We'll wander through ancient, spiral arms that slowly sweep through space like cosmic clockwork, each rotation taking over 200 million years to complete. We'll encounter the invisible dark matter that holds our galaxy together like a gentle, unseen embrace, and we'll visit the supermassive black hole at our galaxy's heart, not as a destroyer, but as a quiet anchor around which hundreds of billions of stars dance in their eternal, patient orbits. Our journey will reveal the stories of stellar nurseries, where new stars are born in clouds of gas and dust, and the peaceful deaths of ancient suns that seed the galaxy with the very elements that flow through your body as you rest. We'll discover how our entire solar system rides a gentle wave through space, bobbing up and down through the galactic plane like a ship on a cosmic ocean. We'll explore the rogue planets that drift freely between the stars, the streams of ancient stars that whisper tales of galactic collisions from billions of years ago, and the faint glow of starlight that takes thousands of years to travel from the galaxy's outer edges to warm your face on a clear night. Each fact will carry you deeper into peaceful contemplation of our place within this magnificent, slowly turning wheel of stars. If this cosmic journey helps your mind find the rest it's seeking, consider sharing this peaceful space with other sleepy souls who might be searching for their own gentle path to slumber. A quiet like or subscription helps other night wanderers discover these astronomical lullabies when they need them most. But for now, let those earthly considerations drift away like distant starlight. This is your time, your rest, your peaceful escape into the vast and patient cosmos. There's no rush, no urgency, just the gentle invitation to let go and float among the wonders that surround us every moment, even as we sleep. The Milky Way has been turning its slow spiral for over 13 billion years. It will continue its patient rotation long after we've all become stardust ourselves. Tonight, you're simply along for the ride, cradled in the gravity well of our cosmic home, safe and small and perfectly insignificant in the most comforting way possible. Here's something that might surprise you as you settle into sleep. Right now, as you lie still and peaceful, you're actually racing through space at over 500,000 miles per hour, not just spinning with Earth's rotation, not just orbiting the sun, but traveling with our entire solar system as it rides the spiral arms of the Milky Way galaxy through the cosmic void, yet you feel perfectly still. This is the beautiful paradox of our galactic home: constant motion that feels like perfect rest, ancient processes that seem timeless, a dynamic system that appears frozen in the night sky. The Milky Way is simultaneously the most stable thing we know and the most dynamic, a galaxy that has been recycling stars and gas and dust for 13.6 billion years, yet appears unchanging across human lifetimes. Every atom in your body was forged in the heart of an ancient star that lived and died somewhere within this galaxy's spiral arms. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was scattered into space by stellar winds and supernova explosions that occurred millions or billions of years ago. You are quite literally made of the Milky Way, assembled from its ancient stellar ashes, animated by its nuclear fire, cradled in its gravitational embrace. The galaxy stretches across 100,000 light years of space, but from our perspective, embedded within one of its spiral arms, it appears as nothing more than that faint band of light that arcs across the darkest night skies. Ancient cultures saw it as a river of milk, a celestial path, a cosmic tree, never guessing that they were looking into the deep structure of their own cosmic home from the inside. Tonight, as we drift through 100 facts about this magnificent spiral of stars, we'll discover that the Milky Way is not just our address in the universe, but our partner in an eternal dance. It shapes our seasons through its tidal forces. It provides the raw materials from which planets form. It regulates the rate of star formation that determines the very possibility of life. We orbit not just the sun, but the galaxy itself, riding a gentle wave through space that carries us up and down through the galactic plane every 60 million years or so. The Milky Way is patient, ancient, vast, and gentle. Its processes unfold across timescales that dwarf human civilization, yet it provides the stable, nurturing environment that has allowed life to emerge and flourish on countless worlds. As you rest tonight, let yourself sink into the comforting realization that you are held safely within something far greater than yourself, a galaxy that has been your home since before you were born and will continue to be your cosmic address long after you've returned to stardust. Our galaxy weighs approximately 1 trillion times as much as our sun, yet most of this mass remains invisible, composed of dark matter that neither emits nor absorbs light. This invisible scaffolding holds our galaxy together with the gentlest possible touch, providing just enough gravitational embrace to keep hundreds of billions of stars in their slow, eternal dance. The dark matter halo extends far beyond the visible spiral arms, creating a cocoon of stability that has allowed our galaxy to maintain its elegant shape for billions of years. Like a cosmic cradle, this unseen mass rocks our solar system gently through space, maintaining the delicate balance that has made life possible. The Milky Way rotates like a vast celestial carousel, but not as a solid wheel. Different parts move at different speeds in a phenomenon called differential rotation. Our solar system, located about 26,000 light years from the galactic center, completes one full orbit every 220 to 250 million years. This means that since Earth formed 4.5 billion years ago, we've made roughly 20 complete trips around the galaxy. Each cosmic year brings us through different regions of space, past different stellar neighborhoods, through varying densities of cosmic dust and radiation. Yet the journey is so gentle and vast that we feel only perfect stillness. Despite spanning 100,000 light years across, the Milky Way's main disk is remarkably thin, only about 1,000 light years thick, making it proportionally thinner than a compact disk. This cosmic pancake is where most of the galaxy's stars reside, concentrated into spiral arms that sweep through space like frozen waves. Above and below this disk, the galaxy extends into a spherical halo populated by ancient globular clusters, tight balls of old stars that orbit through the galaxy's outer reaches like cosmic lighthouses. The thinness of our galactic home means that when we look up at the night sky, we're gazing along the plane of the disk, seeing the accumulated light of billions of distant stars stretched across the celestial dome. Our entire galaxy drifts through space at approximately 1.3 million miles per hour, carried by the expansion of the universe and the gravitational pull of distant galactic clusters. Yet this motion is so smooth and constant that it feels like perfect rest. We're passengers on a cosmic ship that has been sailing through the universe for over 13 billion years, and our journey continues with such gentle momentum that the stars appear fixed in their patterns night after night. This stability allows us to navigate by starlight, to track the seasons by constellations, to feel anchored even as we hurtle through the infinite depths of space at incomprehensible speeds. The Milky Way's gravitational influence extends far beyond its visible edges, creating tidal forces that gently rock our solar system up and down through the galactic plane every 62 million years or so. This cosmic tide is so gradual that it takes 31 million years to carry us from the galactic plane to our maximum height above it, then another 31 million years to bring us back down and through to the other side. Some scientists theorize that this gentle bobbing motion may correlate with periodic increases in comet impacts and mass extinction events on Earth. As we pass through the denser regions of interstellar material, but even these dramatic sounding effects unfold so slowly that they feel like the gentlest possible cosmic rhythm. Dark matter makes up approximately 85% of the Milky Way's total mass, yet we cannot see it directly. We know it exists only through its gravitational effects on visible matter. This invisible component forms the backbone of our galaxy, creating the scaffolding upon which the luminous spiral arms are built. Like a cosmic ghost, dark matter permeates every cubic inch of space around us, streaming through our bodies and through the Earth at every moment without interaction. It neither shines nor casts shadows, neither heats nor cools. Yet without its gentle gravitational guidance, our galaxy would have flown apart long ago. It is the silent partner in our cosmic dance, the unseen foundation of everything we can observe. The space between stars in our galaxy is not empty and cold, but filled with a thin, hot medium called the interstellar plasma, heated to temperatures of millions of degrees. Yet because this gas is so incredibly tenuous, less dense than the best vacuum we can create on Earth, it poses no threat to planets or spacecraft passing through it. This hot, rarefied medium fills vast bubbles blown by stellar winds and supernova explosions, creating a complex network of cavities and shells that shape the galaxy's three-dimensional structure. It's like a cosmic spider web of superheated gas, so delicate and dispersed that it can only be detected by the most sensitive instruments. Yet it plays a crucial role in the galaxy's ongoing star formation and chemical evolution. The Milky Way possesses a galaxy-wide magnetic field that threads through the spiral arms and extends into the halo, providing a gentle organizing influence on the charged particles that drift between the stars. This magnetic field is incredibly weak by terrestrial standards, roughly 100,000 times weaker than Earth's magnetic field, yet it spans the entire galaxy and helps channel the flow of cosmic rays and interstellar gas. Like invisible rivers in space, magnetic field lines guide the motion of charged particles and influence the formation of stars in molecular clouds. This galactic magnetism creates a subtle order within apparent chaos, a hidden structure that astronomers are only beginning to understand through radio observations of polarized starlight. Our galaxy's disk is not perfectly flat like a dinner plate, but instead warped like a vinyl record left in the sun, with the outer edges bending both above and below the main galactic plane. This warp becomes more pronounced toward the galaxy's outer edges, where the gravitational influence of the central bulge weakens and other forces begin to dominate. The warp may be caused by interactions with satellite galaxies or by the influence of intergalactic magnetic fields, but its exact origin remains mysterious. Like a slow-motion cosmic dance, this warping changes over time, causing waves to propagate through the galactic disk over millions of years. The effect is so gradual and gentle that it adds character to our galaxy's shape without disrupting the orderly motion of stars within the disk. Much of what we know about the Milky Way's structure comes not from visible light, but from radio waves emitted by hydrogen gas throughout the galaxy. Hydrogen, the most abundant element in the universe, emits a characteristic radio signal with a wavelength of 21 centimeters when its electron flips from one energy state to another. This gentle whisper from the cosmos allows astronomers to map the galaxy's spiral structure, measure the rotation of gas clouds, and peer through the cosmic dust that obscures our view in visible light. Radio telescopes around the world listen constantly to these faint hydrogen songs, building three-dimensional maps of our galaxy's hidden architecture through the patient accumulation of cosmic static. Light from the most distant stars in our galaxy has been traveling toward us for over 50,000 years, carrying messages from an era when humans were just beginning to spread across the Earth. These ancient photons have journeyed through countless changes in the galaxy's structure, past stellar births and deaths, through varying densities of interstellar dust and gas, yet they arrive at our eyes unchanged, perfect messengers from a distant past. The photons that strike your retina when you gaze at the Milky Way on a dark night began their journey before the first human settlements, before agriculture, before written language. They are time capsules of starlight, carrying information about stellar conditions that existed long before recorded history. The Milky Way has been recycling its stellar material for over 13 billion years, with each generation of stars enriching the interstellar medium with heavier elements forged in stellar cores. The oldest stars in our galaxy contain almost no elements heavier than hydrogen and helium, while younger stars like our Sun are enriched with carbon, oxygen, iron, and all the other elements essential for planet formation and life. This cosmic recycling process continues today as dying stars return their processed material to the interstellar medium through stellar winds and explosive death throes. New stars forming today inherit this chemical legacy, making them potential hosts for rocky planets and complex chemistry. The galaxy ages like fine wine, growing more complex and interesting with each passing billion years. Astronomers can determine the age of different regions within the Milky Way by studying the stellar populations they contain. Using the natural clock provided by stellar evolution, massive stars burn through their nuclear fuel quickly and die young, while lower mass stars like our Sun can shine for billions of years. By analyzing the mix of stellar types in any given region, astronomers can determine when that region last experienced active star formation. The galaxy's central bulge contains mostly old, red stars that formed early in the galaxy's history, while the spiral arms host a mix of ages with active star-forming regions, creating new blue giants that illuminate their surroundings. This stellar archaeology reveals the galaxy's complex formation history and ongoing evolution. Processes that seem catastrophically fast in human terms unfold with cosmic patience when viewed on galactic timescales. A supernova explosion that destroys a star in seconds represents the culmination of millions or billions of years of steady nuclear burning. The collision of molecular clouds that triggers new star formation occurs over millions of years. Even the rapid changes we observe in stellar nurseries represent processes that have been unfolding since before our species existed. This temporal perspective provides a deeply calming view of cosmic change. Everything that seems urgent and dramatic from our perspective is actually part of gentle, patient processes that unfold across deep time. The galaxy teaches us about the virtue of cosmic patience. The beautiful spiral arms of the Milky Way are not permanent structures composed of specific stars, but rather density waves, regions where stars and gas temporarily crowd together as they orbit the galactic center. Like cars backing up behind a slow-moving truck on a highway, stellar material accumulates in these spiral regions, creating the enhanced brightness that traces out the galaxy's elegant arm structure. Individual stars drift in and out of the spiral arms over millions of years, but the pattern itself persists, maintained by gravitational resonances and the galaxy's rotation. This means that the spiral arms are more like cosmic weather patterns than solid structures, persistent features that emerge from the complex dynamics of hundreds of billions of orbiting stars, beautiful and ephemeral at the same time. Just as planets have habitable zones around their stars where liquid water can exist, the Milky Way itself has a galactic habitable zone, a region where conditions are suitable for the development of complex life. Too close to the galactic center, and frequent supernova explosions and intense radiation would sterilize planetary surfaces. Too far out in the galactic halo, and there wouldn't be enough heavy elements to form rocky planets. Our solar system sits in what astronomers call the Goldilocks zone of our galaxy. Not too hot, not too cold, but just right for the patient development of life over billions of years. This cosmic sweet spot has provided the stable environment necessary for evolution to craft the incredible complexity we see on Earth today. Despite containing hundreds of billions of independently orbiting stars, the Milky Way maintains its elegant spiral structure through the subtle influence of gravitational resonances and density waves. Like dancers responding to music they can barely hear, stars throughout the galaxy adjust their orbits in response to the faint gravitational signals from spiral arm patterns and the central bar structure. This spontaneous organization emerges from chaos. No central intelligence directs the galaxy's shape, yet beautiful patterns arise naturally from the complex gravitational interactions of countless stellar orbits. It's a cosmic demonstration that order can emerge from apparent randomness. That beauty can arise spontaneously from the patient working of natural forces over deep time. At the center of the Milky Way lies not a simple spherical bulge, but an elongated bar structure composed of old stars that rotates as a rigid body every few 100 million years. This galactic bar extends roughly 27,000 light years from end to end and helps channel gas from the outer regions toward the galactic center, feeding star formation in the central regions. The bar's gravitational influence shapes the orbits of stars throughout the inner galaxy and may be responsible for triggering the spiral arm structure that gives our galaxy its characteristic appearance. Like a cosmic stirring spoon, the central bar helps mix and organize the galaxy's contents, creating the complex dynamics that maintain the Milky Way's structure over billions of years. Scattered throughout the Milky Way's halo are faint stellar streams, the tidally disrupted remains of small galaxies and star clusters that were torn apart by our galaxy's gravitational forces over billions of years. These streams trace out the orbital paths of their parent objects, creating ghostly rivers of stars that remember ancient gravitational encounters. The Sagittarius stream, for example, wraps around our entire galaxy multiple times, marking the slow death spiral of a small galaxy that has been gradually shredded by the Milky Way's tidal forces. These stellar streams are cosmic fossils preserving evidence of our galaxy's violent past in the form of scattered stars that still follow the gravitational memory of their destroyed homes. The Milky Way operates as a vast recycling center, constantly processing and reprocessing stellar material through cycles of star formation, stellar death, and regeneration. Gas clouds collapse to form new stars, which fuse light elements into heavier ones in their cores, then return enriched material to the interstellar medium through stellar winds and explosive deaths. This processed material mixes with pristine hydrogen and helium from the intergalactic medium, creating new generations of stars with increasingly complex chemistry. The galaxy has been running this cosmic recycling program for over 13 billion years, gradually converting the simple primordial elements from the Big Bang into the rich periodic table of elements we see today. Every breath you take contains atoms that have been processed through multiple generations of stars. The Milky Way is not alone in space, but rather the dominant member of a small group called the local group, engaged in gravitational dances with its cosmic neighbors. The Andromeda Galaxy, our nearest large galactic neighbor, approaches us at roughly 68 miles per second and will merge with the Milky Way in approximately 4.5 billion years. This cosmic collision sounds violent, but it will actually be a gentle merger. The vast distances between individual stars mean that direct stellar collisions will be extremely rare. Instead, the two galaxies will dance around each other for billions of years, their spiral arms intertwining and reforming, ultimately creating a new elliptical galaxy that astronomers have playfully dubbed Milkometa. Above and below the Milky Way's disk, astronomers have discovered vast structures called the Fermi bubbles, enormous cavities of hot, thin gas that extend 25,000 light years above and below the galactic center. These bubbles may have been inflated by ancient episodes of intense activity from the supermassive black hole at our galaxy's heart, or by bursts of star formation that drove powerful galactic winds. Like cosmic soap bubbles, these structures demonstrate that our galaxy has experienced periods of dramatic activity in its past, launching material far beyond the main disk in spectacular fountains of energy. The bubbles continue to expand even today, carrying processed material from the galaxy's interior to its outer reaches, threaded throughout the Milky Way's spiral arms are magnetic field lines that channel the flow of charged particles and influence the formation of new stars. These invisible magnetic rivers help organize the chaotic motions of interstellar gas, creating filamentary structures where molecular clouds can form and fragment into stellar nurseries. The galaxy's magnetic field also deflects cosmic rays, high-energy particles from distant sources, creating a partial shield that reduces the radiation environment around stars and planets. Like a cosmic nervous system, these magnetic field lines connect distant regions of the galaxy, allowing energy and information to flow between stellar systems across vast distances of space and time. Every element heavier than hydrogen and helium in your body was manufactured in the interior of a star somewhere within the Milky Way. Different types of stars produce different elements. Massive stars forge oxygen, silicon, and iron in their cores before exploding as supernovas, while lower mass stars create carbon and nitrogen through gentler processes. The most extreme stellar deaths, when neutron stars collide, create the heaviest elements like gold and platinum through rapid neutron capture. The galaxy serves as a vast chemical factory, with billions of stellar furnaces working constantly to transform simple hydrogen into the complex array of elements that make planets, oceans, and life possible. The calcium in your bones was forged in stellar fire billions of years ago. Orbiting in the distant reaches of the Milky Way's halo are globular clusters, spherical collections of hundreds of thousands of ancient stars that formed early in the galaxy's history. These clusters are among the oldest objects in our galaxy, some containing stars over 12 billion years old, making them nearly as old as the universe itself. Despite containing so many stars packed into such small volumes, globular clusters are remarkably stable, held together by their own gravity for billions of years. They serve as cosmic laboratories where astronomers can study stellar evolution in pristine environments and as probes of the galaxy's early formation history. Like ancient cities orbiting our galactic metropolis, these clusters preserve the memory of the Milky Way's youth. Molecular clouds throughout the Milky Way expand and contract in slow, cosmic breathing patterns that span millions of years. These vast regions of gas and dust, some stretching hundreds of light years across, respond to the gentle pressure waves that propagate through the galaxy as spiral arms pass by. When compressed, they fragment into smaller clumps that can collapse to form new stars. When expanded, they disperse their material back into the interstellar medium. This galactic respiration creates a rhythm of star formation that has persisted for billions of years, ensuring a steady supply of new stars to replace those that grow old and die. The galaxy inhales primordial hydrogen and exhales processed starlight in an eternal cycle of cosmic renewal. Each successive generation of stars in the Milky Way inherits a more complex chemical legacy from its predecessors. The first stars, called Population 3, formed from pure hydrogen and helium and have never been directly observed. They lived fast, died young, and disappeared billions of years ago. Population 2 stars, found primarily in the galactic halo and globular clusters, contained trace amounts of heavier elements produced by their vanished predecessors. Population I stars like our Sun, concentrated in the galactic disk, are metal-rich by cosmic standards, containing enough heavy elements to form rocky planets and complex molecules. This chemical evolution continues today, with each stellar death slightly enriching the galaxy's inventory of elements necessary for increasing complexity. The magnificent spiral structure of the Milky Way is maintained by density waves, self-sustaining patterns of compression that rotate through the galaxy's disk like ripples on a cosmic pond. These waves don't transport material, but rather compress and rarefy the gas and stars already in orbit, creating the alternating bright arms and dark lanes that give spiral galaxies their characteristic appearance. Stars are born preferentially in the compressed regions, creating chains of hot, blue stars that trace out the spiral pattern before dispersing into the general stellar population. The spiral pattern rotates at a different speed than the individual stars, allowing the galaxy to maintain its elegant structure, even as its stellar contents constantly circulate through the arms. Dark matter provides the invisible foundation upon which the Milky Way's visible structure is built, creating a vast spherical halo that extends far beyond the galaxy's luminous components. This dark matter halo contains roughly 10 times more mass than all the stars and gas in the galaxy combined, yet remains utterly transparent to electromagnetic radiation. Computer simulations suggest that dark matter halos have complex substructure, containing smaller clumps and streams that record the chaotic merger history of galaxy formation. Some of these dark matter subhalos may have captured small amounts of ordinary matter to form the faintest dwarf galaxies we observe today, while others remain completely dark, ghostly gravitational structures that influence stellar motions without ever revealing themselves directly. The Milky Way operates a vast circulation system that moves material vertically between the galactic disk and the surrounding halo in a process called the galactic fountain. Massive stars and supernovae heat the interstellar gas in the disk, driving it upward in hot, expanding bubbles that can reach heights of several thousand light years above the galactic plane. As this hot gas cools and condenses, it falls back toward the disk like cosmic rain, carrying with it the heavy elements manufactured by stellar nucleosynthesis. This vertical mixing helps distribute the products of stellar evolution throughout the galaxy and regulates the rate of star formation by removing raw material from the disk and later returning it in a more chemically enriched form. Deep within the densest regions of molecular clouds, gravity slowly compresses gas and dust until nuclear fusion ignites in the hearts of newborn stars. But this stellar birth process is surprisingly violent and chaotic. Young protostars launch powerful jets of material at speeds of hundreds of kilometers per second, carving cavities in their birth clouds and announcing their arrival with brilliant shock-heated gas. These stellar jets can extend for light years from their sources, creating the beautiful Herbig-Haro objects that trace out the early stages of stellar evolution, like cosmic fireworks celebrating new stellar births. These jets illuminate the hidden stellar nurseries throughout our galaxy, revealing the dynamic processes that create the next generation of stars and planets. Scattered throughout the Milky Way are the remnants of stellar death, white dwarf stars, neutron stars, and black holes that mark the final stages of stellar evolution. White dwarfs, the cooling embers of stars like our Sun, are so dense that a teaspoon of their material would weigh as much as a car. Neutron stars pack the mass of the Sun into a sphere only 12 miles across, creating gravitational fields so intense that they bend space-time itself. Stellar mass black holes represent the ultimate gravitational collapse, regions where matter has been compressed to infinite density. These stellar corpses dot the galaxy like cosmic tombstones, yet they continue to influence their surroundings through gravity and occasional outbursts of energy when matter falls onto their surfaces. Stars throughout the Milky Way ring like cosmic bells, vibrating with acoustic oscillations that reveal their internal structure. To astronomers who practice the art of asteroseismology, these stellar vibrations, caused by sound waves bouncing around inside stellar interiors, create tiny variations in brightness that can be detected by sensitive instruments, just as geologists use seismic waves to probe Earth's interior structure. Astronomers use stellar oscillations to map the cores of distant stars, measuring their ages, masses, and internal rotation rates. The galaxy hums with the acoustic signatures of billions of stars, each contributing its own unique frequency to the cosmic symphony that tells the story of stellar interiors hidden from direct observation. As stars like our Sun age and exhaust the hydrogen fuel in their cores, they swell into red giant stars hundreds of times their original size, becoming so large that they could engulf the orbit of Mars. These aging stars pulsate gently, losing mass through stellar winds that carry processed material back to the interstellar medium at speeds of just a few kilometers per second. Over millions of years, red giants can lose half their mass or more, enriching the surrounding space with carbon, nitrogen, and oxygen forged in their nuclear furnaces. This gentle stellar death creates some of the most beautiful objects in our galaxy, planetary nebulae that glow with the light of hot, white dwarf stars illuminating the shells of gas they've expelled. During their final evolutionary stages, the Milky Way has been running an efficient stellar recycling program for over 13 billion years. with each generation of stars incorporating material processed by their predecessors and adding their own nuclear products to the galactic inventory. Massive stars live fast and die young, exploding as supernovae that scatter their nuclear ashes across vast regions of space. Lower mass stars, like our Sun, live longer, but eventually return their outer layers to the interstellar medium through gentler stellar winds. This continuous recycling process has gradually increased the galaxy's metallicity, the abundance of elements heavier than hydrogen and helium, making possible the formation of rocky planets and the complex chemistry required for life. Carbon, the foundation of all life as we know it, is manufactured primarily in the cores of aging stars through a process called the triple alpha reaction, where 3 helium nuclei combine to form a carbon nucleus. This nuclear reaction requires precisely the right conditions of temperature and density, and was impossible in the early universe when the first generation of stars lacked the heavy elements needed for efficient energy production. As these early massive stars died and enriched the interstellar medium with heavier elements, subsequent generations of stars became increasingly efficient at producing carbon and other elements essential for complex chemistry. The carbon atoms in your DNA were forged in stellar furnaces billions of years ago, then scattered into space to become part of the molecular clouds from which our solar system eventually formed. Silicon, the second most abundant element in Earth's crust and the foundation of modern technology, is produced primarily in the cores of massive stars during their final moments of nuclear burning. These stellar furnaces operate at temperatures of billions of degrees, hot enough to fuse lighter elements into silicon through a complex series of nuclear reactions called silicon burning. When these massive stars explode as type 2 supernovae, they scatter their silicon-rich interiors across vast regions of space, seeding future generations of star formation with the raw materials for rocky planet formation. The silicon chips that power our computers and smartphones contain atoms that were forged in the violent deaths of massive stars that lived and died billions of years before our solar system formed. The iron flowing through your veins right now was created in the final seconds of a massive star's life during the catastrophic core collapse that triggers a supernova explosion. Iron is the most stable atomic nucleus, requiring enormous energy inputs to create and representing the endpoint of efficient stellar nucleosynthesis. When a massive star's core is converted to iron, it can no longer sustain nuclear fusion, leading to gravitational collapse and the violent explosion that disperses iron-rich material throughout the galaxy. Each iron atom in your hemoglobin carries the memory of stellar death, a cosmic sacrifice that makes oxygen transport through your bloodstream possible. The iron in our galaxy has been accumulating for billions of years through countless stellar explosions, gradually enriching the interstellar medium with this essential element. The gold in your jewelry and the platinum in catalytic converters were created not in ordinary stellar cores, but in the most extreme cosmic collisions, the mergers of neutron stars, or the collisions between neutron stars and black holes. These cataclysmic events, which occur perhaps once every few thousand years in a galaxy like ours, create conditions hot and dense enough to forge the heaviest elements through rapid neutron capture processes. In just seconds, these cosmic collisions can produce more gold than our sun could manufacture if it burned for billions of years. The recent detection of gravitational waves from neutron star mergers has confirmed these events as the primary source of gold, platinum, and other precious metals scattered throughout our galaxy. Lithium, one of the lightest elements and crucial for modern battery technology, presents one of the biggest mysteries in galactic chemistry. While the Big Bang should have produced a specific amount of lithium in the early universe, observations of old stars in our galaxy show much less lithium than expected. This lithium problem suggests that stellar interiors destroy lithium more efficiently than predicted, or that unknown processes in the early universe modified the primordial abundance. The missing lithium represents a cosmic puzzle that connects the formation of the first elements in the universe to the chemical evolution of our galaxy, reminding us that even the simplest processes in stellar nucleosynthesis still hold secrets waiting to be discovered. More than half of all stars in the Milky Way exist not as solitary objects like our Sun, but as members of binary or multiple star systems locked in gravitational embraces that can last for billions of years. These stellar partnerships range from tight binaries, where stars orbit each other every few hours, to wide binaries separated by thousands of astronomical units, with orbital periods measured in millions of years. Some binary stars are so close that they actually touch, sharing material in a cosmic dance that can lead to spectacular novae when matter from one star accumulates on the surface of its companion. Others maintain respectful distances, aging gracefully together like an old married couple, their mutual gravity providing stability and companionship across cosmic time. Throughout the Milky Way's halo, faint streams of stars trace the orbital paths of disrupted star clusters and small galaxies that have been torn apart by our galaxy's tidal forces. The Sagittarius stream, for example, wraps around our entire galaxy like cosmic ribbon, marking the slow death spiral of a dwarf galaxy that has been gradually shredded over billions of years. These tidal streams are so faint that they contain only a few stars per cubic light year, yet they extend for tens of thousands of light years across the sky. Like cosmic archaeological evidence, these streams preserve the memory of ancient gravitational encounters and help astronomers reconstruct the violent merger history that built our galaxy into its current massive form. The Milky Way's magnetic field creates invisible highways that channel the flow of cosmic rays. High